So I think we'll get started for today. Before I begin, are there any questions lingering from anything we covered yesterday? So if you recall, we talked about a few sort of foundational concepts yesterday. We talked about composition and layout to begin with. We talked about Gestalt Principles of perceptual organization, hierarchical organization, things like that. From there, we moved on to talking about different plot types. Talked about how we might taxonomize different plot types, different charts and graphs. After that, we spent some time talking about color and specific color considerations we have to make when we're creating visualizations, especially around color blindness, for example, and different kinds of color palettes. Today, we're going to move on to a wider variety of topics. So we're going to start by talking a bit about improving figure clarity, some special considerations and tips and tricks for improving particular kinds of visualizations. Then we'll talk a bit about heat maps, making heat maps in Ggplot 2. We'll have a lunch break. After that, we'll talk about multidimensional data, different ways of working with high dimensionality. And then we'll talk about data exploration, linked views, things like that. And we'll finish the day off with visualization critiques. So we'll sort of combine everything we've talked about, all the concepts we've covered in the past 2 days, and apply that to looking at real-life, real-world visualizations in the scientific literature and coming up with improvements to those and critiques for those. Okay? So we're going to start today by talking about improving figure clarity. And the whole point of this session is to really understand the importance of simplifying charts and graphs in order to aid communication. So that's why we improve figure clarity to aid communication when we're creating a visualization. Yesterday, I mentioned someone by the name of Edward Tufte. He, as I said before, is sort of regarded as one of the fathers of data visualization. He writes quite a bit on best practices, best design practices in visualization. He's most well known for these 2 books, Visual Display of Quantitative Information and Envisioning Information. And in these books, he talks a lot about graphical integrity. So he says things like, clear, detailed, and thorough labeling should be used to defeat graphical distortion and ambiguity. Write out explanations of the data on the graphic itself, label important events in the data. And this is from Visual Display of Quantitative Information. He goes on to talk about 6 different roles for graphical displays. I mean, you can think of a graphical display as essentially a visualization, any sort of visual communication of information. The first of these roles is that any graphical display or visualization should first and foremost show the data. This seems obvious, but we've all encountered visualizations where data are obscured for whatever reason. Second role is that graphical displays should avoid distorting what the data have to say. So this goes back to my comments about ethical design yesterday. This idea that when we create a visualization, we should always make sure that it's reflective of the behaviors and patterns in the data themselves. Graphical displays should encourage comparisons. So we talked about 3 axioms of effective design, one of them being that good design, good visualizations encourage discovery, facilitate discovery. Fourth role is that graphical display should reveal the data at several levels of detail. So we can think about this in terms of close reading and distant reading. We can sort of interpret a set of data at multiple levels of resolution, and it's up to us to decide at what level we want to present and communicate information. Graphical displays should serve a reasonably clear purpose, so we should be very intentional in our designs of visualizations. And finally, graphical displays should be closely integrated with the statistical and verbal descriptions of the data themselves. There's one concept in particular that he's widely known for, and that's something called the data ink ratio. And this is actually a mathematical ratio, and it's defined as the proportion of ink used to communicate data in the visualization divided by the total ink used to print the graphic. So it's not always the case that all of the ink used to create a visualization is used to actually communicate the data themselves or represent the data themselves. Put another way, we can think of this as sort of a curve with respect to data ink complexity on one axis and meaning or value on another. The idea being that as we increase the data, ink, or complexity of a visualization, we see increases in the meaning and value of the visualization, but only up to a certain point, right? As we increase past a certain point in terms of data or ink complexity, we start seeing diminishing returns. And that's because the visualization becomes much more difficult to understand and interpret. We're actually increasing the cognitive load placed on the user to interpret the visualization. So we sort of want to strive for reaching this sweet spot between complexity and the meaning and value of a visualization. This is an example of an infographic that has a very low data ink ratio. So there's lots of ink in this infographic used to represent a lot of sort of graphical elements that don't actually communicate the data. So if we look here, we see the data is represented only by essentially these numeric markers here. Some graphical markers, I guess these triangular shapes are supposed to represent proportions as well. But the vast majority of ink used to create this infographic is not used to actually communicate the data. We might contrast that with a visualization like this. This is a Ggplot map showing homicide counts in the Boston metropolitan area. And this has a very high data ink ratio because essentially all of the ink used to produce the graphic is used to actually communicate the data themselves. So here we have shading zip code areas based on relative counts of homicides. So we can use this data ink ratio as a sort of guideline for thinking about when we're designing a visualization effectively or well. Can you think of a situation where a data ink ratio is not a good measure of effectiveness? What if I were to show you a visualization like this? So this has very high data ink ratio. Essentially all of the ink used to produce the graphic is used to communicate the data themselves, but it's also very difficult to read, right? It's just very complex. Here's another example. Very high data ink ratio, but also very difficult to read, right? It's difficult to make comparisons across categories. So we have to be careful about using the data ink ratio as a universal measure of effectiveness for visualizations. It's useful, though, in other contexts when we think about what data ink ratio means when working within software defaults. So we've encountered this a bit already when working with Ggplot, right? When we create visualizations in different platforms, so say Ggplot 2, for example, or even in Excel, software defaults aren't always designed with simplification in mind. So if we look at some examples from Ggplot 2, here's a bar chart. We've got some extra grid lines in there that we don't necessarily need. Scatterplot, same thing, some extra grid lines. We could clean it up with better labeling, for example. And a line chart, extra grid lines. We can clean up the tick marks on this bottom axis. Could increase the extent of the tick marks on the vertical axis as well. So we always have to be careful when working within software defaults because they're not always going to be designed with our best interests in mind, especially with respect to simplifying figures and improving figure clarity. So I'm going to spend a little bit of time now talking about some simple tips for improving basic charts, a variety of sort of miscellaneous tips, also generalizable tips. And in general, they're going to fall within these three categories. So the first sort of overall tip that we can use to simplify graphics is reduce the number of elements, right? This is pretty simple. We create a visualization, we can always reduce excessive elements, excessive tick marks, excessive lines, grid marks, things like that in a visualization. Because fewer elements means fewer bits to process, lower cognitive load for the user. We can use Gestalt Principles. So we talked about these laws of perceptual organization yesterday. And we can really leverage these laws around alignment, spacing, grouping, and hierarchy to improve the clarity of our figures. And the final sort of category or general tip is that we can use strong visual encodings. So position, length, proportion, hue, and all those other kinds of channels that we talked about yesterday, we can leverage those to improve the clarity of a figure. So let's talk about some of these in detail. The first thing we can do is use contrasting visual encodings to enhance the salience of particular data elements in a figure. As a reminder, these are all the different kinds of visual encodings that we talked about yesterday. So these are channels. We talked about marks, which are sort of basic graphical elements, and then channels, which are ways of modifying the appearance of marks. So these are all different kinds of encodings that we can use in the visualization. And we can really leverage these and contrasts between them to increase the salience of particular data points. So let's say I have this sequence right here. It's very easy to pull out instances of the letter A because it's red, right? It stands out very clearly. But it's not so easy to pull out instances of the letter P, right? So here we're using color as a medium for increasing the salience of the letters A in this figure. Okay. We can use redundant encodings to aid perception. We talked a little bit about this yesterday as well when we talked about color, using color redundantly to encode information. But we have to be careful because redundancy comes with a conjunctive visual search cost, right? If we're using too many redundant encodings for a particular data points, we're asking the user to keep too many pieces of information in mind at once when they're interpreting a graphic. Here's an example of that in action. So here in figure A, we have a figure that is combining a wide variety of mark appearances. So we have different symbols here. We have different colors to indicate different classes. And we have different stroke widths here, so thin versus thick. And it's difficult for the user to read this figure and sort of get an immediate impression from it because they have to go back to try and figure out what do these combinations of marks mean, what do these combinations mean, what do all three of them mean together, right? It's difficult to sort of keep all of that in mind. Here we have a modification of this first chart. We've split it out into two panels, and we've simplified and reduced the number of ways in which we're redundantly encoding information. So here we have two different kinds of shapes only, and we have color as a differentiator. And then here we have essentially two overall types of shapes, and we're using orientation to indicate different mutations. So we can leverage these different kinds of visual encodings effectively as long as we're careful not to use too many of them at one time. Another tip, avoid any unjustified use of 3D representation. Michelle talked about this a little bit yesterday in her keynote. We've probably all seen charts that look like this, right? Unnecessarily three-dimensional bar charts, when the two-dimensional version is much more effective and much simpler. What are some reasons why 3D bar charts in particular might not be useful? What's bad about using unjustified three-dimensionality in a bar chart? So it obscures comparison because we have this perspective effect that influences the way that we can draw those comparisons. And we'll talk a little bit more about this a bit later. Also, if you sort of look at this from the data ink ratio perspective, it's unnecessary extra ink in the graphic that doesn't really aid any communication of information. Data labels. So use data labels judiciously and position them without obscuring important parts of the visualization. We work a lot with data labels, especially in scientific visualization. So here are some examples of good and poor label placement. Here we have poor label placement because it's difficult to tell which labels correspond with which data points. We also have some inconsistency in alignment and positioning and spacing of those labels. data points and their labels. Here's another example of data label placement. So we have two figures. At the top, we have a wide variety of orientations, angles, geometries, of callout labels. On the bottom here, we sort of clean things up where we've limited things to just horizontal lines for our labels. We've improved the relative spacing between the ends of line segments and their labels. So we've introduced some consistency into our use of data labels in the bottom figure. Marker types. So for dense plots that have lots of points in them, use open markers instead of closed. So this might be hard to see with the resolution of this projector. But we have pretty high density down in this part of the plot, lower density in that part of the plot. And we have a variety of kinds of markers here. So we have different shapes. We also have closed or filled markers and open or unfilled markers. Who can give a guess as to why open, unfilled markers are better for dense plots? Yeah.
It gives you a better sense of how many points are actually there and you can pick out individuals.
So you don't obscure data points that might be close to one another without overlapping. Of the four shapes shown here, which of these four open shapes do you think is best for encoding dense plots? Which do you see most often in figures? Circle? Open circles are actually one of the best markers to use. And the reason is that the circle is the only shape of these four that doesn't produce or reproduce an image of itself when multiple symbols overlap. So you overlap multiple open circles, you don't get another open circle within it. The same can't be said about triangles though, because when you overlap triangles, you get more triangles. Same with squares, same with crosshairs. So if you have a very dense plot and you're using these other kinds of markers, you can actually make it seem as though there's more data there than there actually is. Okay, so open circles are ideal. When you do have to use a wide variety of shape markers, choose combinations of shapes that have strong visual boundaries. So this means that if you're positioning multiple shapes next to each other on a dense plot, make it easy to distinguish between those different shapes. So the top row here is a collection of shapes and marks with strong visual boundaries. So we have circles and pluses, crosshairs. We have different stroke widths. We also have the use of color. So color is an excellent differentiator, excellent strong visual boundary. Second row shows shapes with weak visual boundaries. So we have different orientations of triangles. If you have those next to each other in a plot, it's very difficult to tell the difference between them. We have different orientations of squares, pentagons, things like that. Sometimes in figures we use letters as marks, right? For the most part, this doesn't produce any real problems as long as the letters are visually distinct enough. So here it's relatively easy to tell the difference between these different sort of markers. Sometimes we have to be careful about using shapes that have very different geometries because it might produce perceptual effects in relative sizes. So for example, this circle might appear much larger than this triangle or this star shape. And so that might inform how So if we look at another example of a chart that uses multiple encodings using shapes and color. Here we have a bit of a non-intuitive encoding, different combinations of colors as well as shapes as well as circle enclosures, different marker types. And then in these two, we've sort of brought in some more intuitive encodings. We've simplified the kinds of markers we use. So here we're just using open and closed markers, one type of geometry, and two types of color, and one differentiator of size. So going back to data ink ratio, I mentioned earlier that when we work with software defaults, we often have to sort of wrestle around with extra graphical elements that are output in a visualization. So one way to improve figure clarity is to eliminate or reduce unnecessary default elements, such as grid lines, excessive tick marks. So we look at an example, again, from Ggplot 2, scatter plot here. We can clean things up by getting rid of excess grid lines. We strengthened the axis boundary, stroke width of the axes. And we sort of improved the clarity of the outer bounds of the chart as well. Pie charts are the bane of every visualization designer's existence, but we still use them. So when you need to use or create pie charts, there's a very simple trick that you can follow to make them easier to understand, and that is arranging the two largest wedges of the pie chart at the 12 o'clock position, and then order the remaining ones counterclockwise in descending order. So here's an example. We look at D here. So we have the largest two wedges at the 12 o'clock position, and then we position the remaining wedges in descending order of size counterclockwise around the circle. Here's an actual example that shows that principle in action. We often create visualizations that have lines as markers. So a simple trick we can use to improve the clarity of those figures is to use an aspect ratio that maximizes the extent to which line segments are normalized to a 45-degree angle. So aspect ratio is a calculation of height divided by width for a figure. And the idea is that when we maximize the extent to which line segments sort of bank to 45 degrees, we distribute distortion equally between horizontal and vertical displacement for a line segment, right? So if we look at an aspect ratio of 2 to 1 in this figure here, we've really distorted the behavior of this line segment in the vertical direction. For 1 to 4, we've really flattened out the behavior of that line segment. So this principle is known as the banking to 45-degree principle. We talked a lot about Gestalt principles yesterday, and one way that we can incorporate those into improving figure clarity is by avoiding Gestalt illusions that can engender incorrect readings of a visualization. So for example, we may have all seen this optical illusion. This is based on the Gestalt principle of closure. The idea being here that there's no triangle shape that's explicitly drawn here, but perceptually we fill in that shape because of the contours produced by the surrounding geometries. And we saw that, for example, with a line segment. So if we have a broken line segment, we might be perceptually inclined to join those in our mind. which has implications for null values and how we represent null values. We talked about that yesterday as well. Figure ground illusions also play a role in visualizations, although we might not always be aware of it. So these are some classic optical illusions that we probably have all seen, where figure and ground sort of flip back and forth. Here is an example of a chart where figure and ground have been unnecessarily flipped. So there are a few problems with this visualization. One of which is that the y-axis is flipped in the opposite direction. But the bigger issue is that there's this confusion of what's the figure and what's the ground. And that's because there's this very bold use of red here. So we might be inclined at first glance to read this chart as though the vertical axis starts here and goes upward, as we're normally trained to do them. But because of the use of color, our interpretation of the graph changes unless we look closely. We should be careful of illusions of scale. So these are some more optical illusions you may have seen. Here we have two circles surrounded by different size circles. These two circles are actually the same size, but they appear to be different because of their surrounding geometry. Again, two circles that appear to be different in size, but one is enclosed by another circle, so it appears larger. And then line segments. So line segments that converge upon a common perspective can induce perceptual effects. This is problematic in things like bubble charts. So if we have multiple circular marks in a chart that vary in size, based on the size of surrounding circles, individual data points may appear larger and smaller than they actually are. And that can induce incorrect interpretations of a visualization. So because there are all of these different kinds of Gestalt illusions, we should always be careful to use visual encodings that can be interpreted accurately. And this is actually problematic because not all encodings are made equal, right? We talked a little bit about this in color yesterday specifically, how our discernibility of lightness is much stronger than that of hue or saturation. The same is true for different kinds of channels that we've talked about beyond just color alone. So if I were to show you these two line segments right here, and say this line segment has a value of 4, what would you say this line segment has a value of? 3. If this is 4, what would this value be, do you think? A few more here. 4. Think about what you might expect these values to be. 1. So if we look at the actual values, this is probably the easiest to interpret. These two are probably more difficult. This may have been more difficult than this one. This one was probably okay. This one might have been more difficult. So there's an actual phenomenon attached to this called Weber's law. And Weber's law says that the perceived change in a stimulus is proportional to the initial stimulus. So this is also known as the just noticeable difference. And it refers to the extent to which we have to change a stimulus before a difference can actually be observed. And this is also represented in what's called Stevens' power law. And this is just really a fancy way of saying that we have a wide tendency to overestimate saturation, differences in saturation once you use a mark. We have a tendency darn good at making comparisons using length. So we saw that with the example that we just did, right? It's pretty easy to tell the difference between two lengths and make comparisons between them accurately. Okay? Any questions about any of this? So we're going to do an activity with paper and markers now. We're actually going to spend a bit of time today with paper and markers, so I hope this will be fun. I'm going to have you break up into small groups or pairs. And what I'm going to do is give you a set of data. And in your group, you're going to come up with an interpretation for those data, and then create a visualization that communicates that interpretation. After that, you're going to pass your visualization on to another group, and they're going to create a new derivative visualization that improves upon the visualization that you created. So makes it clearer, makes it easier to understand. We'll repeat this process a few times, and then you'll get your stack of visualizations back, and then we'll talk about them a bit, okay? So this is your data set. It's a set of random integers. So go ahead and find a partner or make a small group. There are markers scattered across the room. There's paper right here. So once you have your group, come get some paper, and then come up with a conclusion or interpretation for the data set here, and draw a visualization of it. Okay? Your interpretation can be anything you want. This could be a class of test scores. It could be anything that you want. It doesn't have to be scientifically motivated. try and wrap up your chart in about 2 minutes. Wrap up in 1 minute. Okay, so take your visualization, pass it on to a group next to you, or exchange. And what you're going to do is take a look at the new visualization you've received. And you're going to create a new visualization based on that and improving upon that visualization that you received. So how can you make the visualization you received clearer, easier to understand? Thinking about not only what we talked about in lecture just now, but also in terms of what we talked about yesterday with composition and layout, hierarchical organization, color, plot types. Maybe a different kind of chart is better to communicate the information. So come up with a new visualization based on what you received. Okay, we're going to do this one more time. Take the chart that you just created, put it on top of the one that you received, so they're a package, they're together, and then pass both of those to another group. Different group if possible. If it's the same, it's okay. So we're going to do this one more time. Look at the visualization or visualizations that you received and come up with one more derivative visualization that improves the clarity of those. try to finish up in about a minute. Okay, wrap up what you were working on. When you're done, take your visualizations and return them to the original group. You can figure out who that is. So once you have your original visualizations and derivative visualizations back, take us a couple minutes to discuss with your partner these questions. So first question is, in what ways was your original visualization improved by other groups? Did you find improvements on your visualization that were surprising? And are there specific ways in which you could have communicated your data more effectively from the very beginning? So did you find some interesting improvements? Were there any improvements that were surprising? So the goal of this exercise was really to show you, again, like we talked about yesterday, the fact that there are many different possible representations for a set of data, right? There are many, many different ways you can visually communicate your data. And so while you may have produced an original visualization that was clear to you, when you give that to another group, that clarity might not always translate through, right? So hopefully this was a useful activity to get you thinking about different ways in which you can actually practically build in improved clarity into your figures using just paper and markers. Whenever we're creating visualizations, we should always be working through an iterative process like this anyway, right? We should always produce a visualization and then come back to it and improve various parts of it, because there are always going to be things that can be improved, okay? Always in terms of composition and layout, in terms of the kinds of marks that we're using to improve the overall clarity of our figures, okay? Any questions about that? Okay. So Ting is going to talk a little bit about improving figure clarity in Ggplot. We may split up some of this hands-on into the next section too, depending on how things go. Yeah. So the next section after the break will be devoted to heat maps, but we'll also use that a bit of overfill time in case we run out of time for this section here.
So I think if you saved the working directory we used yesterday, we can keep working on the same project working directory. If you forgot to save it, you can just as we learned before, new project and move them and like a new project and put the data here, new folder and put the data inside the folder. So we will keep using the same data set, CRC1. And for the hands-on, we will use the hands-on fold, improving the figure clarity. So in this part, we will just practice 4 things. First, as Steven emphasized, when we have like more large number of data points in the figure, the overplotting, the overlapping between the data points will be very serious. So how can we solve this problem? So that's the first issue we will deal with. Second is like I think in Steven's slides, he also mentioned the order bar chart because currently the bar chart is the default is ordered by the letter order, but we want it is ordered by the head of each bar, so ordered bar chart. And also for sometimes we want to see the details of the plot, so we want to zoom in. And the last one is just change the labels. Everything you see in the plot, you can change it. But for the probably we have limited time, so we will just very quickly go over the last part. Our Ggplot tool really plot plenty of options to change it, and you can practice it after class. Okay, then let's go to the first one. So again, before we do the first step, we need to load the package Ggplot2. In today, so in order to make the ordered bar chart, we probably will make some data manipulation. So then we need here we use some two new package called dplyr and tidyr. So we need to load it. When you load the two package, if you have an error show you don't have the package, again you can go to tools, install packages, and install package from here. If you have problem with the two package, installing the two package, just raise your hand and our TA will help you. Okay. So yeah, because today our hands-on will be more complicated, so we couldn't type the code one by one. We'll just go over the code and see what it can do. What can it do? So first, again, we need to read our data set. We call again the same data set, the CRC data set. But as we showed before, the CRC dataset, it only has 72 proteins and 200 samples. In order to show how the overplotting problem, I give another dataset. We call it NCI60. NCI60 is so it contains, I think, 60 cell lines. It's not patient. But it is quantified by SWAS, so it quantifies more than 3,000 proteins. So we just want to show 3,000 proteins in one scatter plot. And okay. Sorry. And again, we also read in the NCI60 dataset. So here just to show you what's the here each cell line is duplicated, so there are two technical replicates, but we just use it to show the overplotting problem, so it doesn't matter. I will go over the code a little bit quicker, so if you have problem, please feel free to stop. So the first thing we just made a very simple scatter plot we have made yesterday. As you see here, it's a very simple one, jump point. So since we only have 200 points in the plot, so the overplotting problem is not very serious, but we still want to show several solutions to the overplotting problem provided by Ggplot2. The first one is, as seen here, is you can we can give a small random movement to move to each point in the plot by geom jitter. So since our plot is already expressed, also the difference is not very obviously, but if you use some like the toy example Yang showed yesterday, you will see it's quite clear how the jitters work. So that's the first option we can use to make to solve the overplotting problem. The second one is but if we go to our new data set, the NCI system, now this time, remember what we plot before. We x is one protein, y is another protein, and each point in the plot is one patient. So in this way, we want to see the distribution of the patients. But actually, we can also, given the same data set, we can also see what's the distribution of different proteins, like here. Now this time, we just plot the x-axis is one cell line. The y-axis is another cell line. And each point in the plot now, let's see, is a protein. So first, again, we make the scatter plot. So in this way, we can see quite different as the two cell lines. They may have some kind of correlation because the two cell lines actually they come from the same tissue, breast, I think. So it's reasonable you can see some correlation between them. Each point in the plot now is one protein. But as you see here, the overplotting is quite serious. We just know there are some points, but how much, like how many points here inside the dark area, we don't know. So we want to have some plot which can tell us if there are more points, the color should be darker. So we can, it's kind of the scatter plot. And in order to make the problem, as we mentioned, to solve the overplotting problem, as we mentioned before, we can use the jitter one, give it some random movement, but still it doesn't work very well because in this we have the data set is large. So there are more than 3,000 points. And then so on the jitter one, it doesn't work very well. So then Ggplot offers us some other options. Again, as Steven mentioned, here all the previous shape we use is just the solid points. But now we want to use some empty in case we can know, like in specific area, how many, like we can have a sense of how many points it has. So then we can change the shape to empty. If you go to the cheat sheet on the back page side, you will see a very low part, second column. There will give you a shape table, which is used in R. And you can choose the shape you like from this table. Now we just use the first shape, which is empty circle. If we use it, if we try to make the shape here, we tell we want empty circle. See, it has given us a better sense of how we can know, better sense of there are much more points inside the dark area. But still, it's not that clear. Like we want something like scatter plot. Another option is you can also change shape, but not change it to the empty, but change it much smaller. So again, so it's just emphasize most of points come from this area. But I feel the more useful option, the last option, Ggplot 2 offer, if you have multiple points in the scatter plot, is the alpha we mentioned before. is to the transparency of the plots. So what does alpha mean? Alpha mean is just a ratio. It means given 3 points, I only want to make 1 point dark. Like 1 point solid dark. So I see, let's try some see the difference. First, we give a bigger alpha. It means among 3 points, we want 1 point become solid. Now let's decrease the alpha. Again, as you see, when you decrease the alpha, the transparent will become more and more because the outliers, the points on the outside will become more and more gray, and only the area which have more points will become dark. It just gives us a sense which area like in the plot has more data points. That's the several options Ggplot2 give us. If when you plot your own data set, you can select like based on the size of your data set, you can select the way from here to show how the distribution is. That's the first one. Okay. Question? Okay. Let's see what type. If no question, we'll go to the outer bar chart. It's I think I can skip it. It just the idea is quite simple. Like let's see our original one. Again, our original bar chart. So it is ordered by the alphabet order of the it's by the letter of the order of the letter. So B, C, H. But we want the order, it is ordered by the head. Then what we can do is, in the previous session, I forgot to mention is, the bar chart here is, it will automatically calculate how many samples under each group. So we don't need to calculate by ourselves and give the number to bar chart. But you can do it like this way, and you give a additional argument is statistics identity. It means you just told Ggplot, I have already calculated the cases in each bar. You don't need to calculate for me. So in order to make an ordered bar chart, we need, so that's why we need to calculate the number of samples in each group by ourselves and order the bar by ourselves and then give the data to Ggplot2. So here, the code here, you can try it after class. It just, let's see. We first calculate the number of samples in each group. But again, as you see here, it's still ordered by the letter. Now we want to change it to ordered. So we want ordered, change it to by the number n. Then we do some data manipulation as here. Now after that, the new data will ordered by the n. So we just make the data, reorder the data based on n. And then if you give the data set now to Ggplot2, Ggplot, it will give you an ordered bar chart. Okay, question? No? So the next one is just we just want to change the limit of x-axis and y-axis. It's quite simple, so I just very briefly. The same all the previous plot we made, we can add one. Let's see. Let's first make, especially for the histogram, we want to. Sometimes we want to, see the middle part of the details in the middle part. So we can just change the x limit. And it's quite easy. We have a function called coordinate Cartesian, and we can change the x limit and y limit inside. Actually, Ggplot2 offers some other options. There are multiple ways to do it. Here, just one way. Change the limit, and you can see more details. So because sometimes you see this kind of figure in many paper as you have a big figure and then it will zoom into a small proportion of the figure and point out. So that's just a way to tell you how to make the local part of the figure. See the local part of the figure. So I think another one is how sometimes we try to emphasize we try to check specific sample, want to see how it looks like. I think one way is if you only want to highlight one sample. That's the code here just tell you how can you highlight one sample. The idea is we still want to use the gel text. So we will give only, okay. So we will only give the text, we will annotate the specific point we are interested in. So let's see what is output. First we have the same scatter plot, but now this time we're just interested in we have some prior information about one sample. We want to see exactly how this sample looks like in the plot. Of course, you can just annotate all the points in the plot, but as we see, if you have many plots, the text will be overlapped. So in this way, we just provide another option to only highlight one sample in the plot and give you. See here as we want to highlight the sample P1, D2. It's a little bit ugly, but so you can change the color, the font, and to make it more clear. Here I just want just see, okay, the sample is in the middle of all the plot, and give you a sense of what's the corresponding protein abundance. That's just to tell you, and the idea is we make a text. So we can give the different color of. We can give a specific different color of we can give different color of that specific sample. So we see if the sample is the sample we're interested in, we just give it a color we call a different group, we call it highlight. If it's not the sample we're interested in, we just tell it it's in the normal group. And when we plot it, we will give a highlight different. The Ggplot2 will automatically give the highlight different color. And we can also add a text, which is just the name of the sample. So if you are interested in how you can make highlight the specific point in the plot, we can discuss it after class. I think what time? Okay. So that's how we highlight a specific point. The last part is quite long, but overall the idea is you can change a lot in the Ggplot2. First thing, I think all the previous slides, see the plot we make, the background is green background. You can change, and there are gray in the background. So sometimes I honestly I don't like the gray, so I always remove it. So then the idea you can change it. So first let's make again. Let's again make a scatter plot. Now this time we want to change like the label, the title, and the legend, and the background, and like the color. So all the appearance you see here. We first can change like add title. So use the labs function. We can add title. You can also add the subtitle and the caption. See here. Then we add title, subtitle, and caption. You can also change the name of the label of the x-axis. Like now we change the label of the axis, and we also change the name of the legend. So you can change the name of the title, x, y axis, and the legend just by the labels. That's the first thing you can change. Second thing is you can, so here, Ggplot 2 offer a very powerful function. We call it theme. And here, let's see. I give a reference of it. If you go to the reference page I gave you, see, that's how the options theme provide. Like you can use this one to change almost everything you see in the Ggplot to accept the data points, the data. So many options. Let's see why actually Ggplot 2 is quite a complicated package. So the first thing, we will just try some important options we are interested in. First, we want to change the background of the plot. That's the original one, the default one, gray one. Now we want to change it to classic. So I just try the options one by one. I really don't like the dark. I don't. Also, that's the one we. Okay. The light one, the background is light white color, and also just remove every background, all the background. And you can also make the background, because the previous one just some default predefined background. We can also define any background we like by the option provided by theme. That's the second one we can change. Another one we can change is just the sometimes as see here, this one is not. When we let's try to make a line chart. If we make the line chart we make before is like here, so we want to see just like we call it profile plot in our analysis is, especially when we have multiple peptides, when we quantify, we want to know the profile for each protein. We want to know its corresponding peptides profile across different samples. So in this way, we can see why we are interested in is we expect that the peptides belonging to the same protein should have the same trend pattern across different samples. So that if you make the profile plot, it's quite easy to see which peptide is like we see has different pattern from other peptides. So this, and you may consider you don't want to use the peptide for the quantification. So we call it profile plot. And here we don't have the peptide data. We'll just profile the two proteins across different samples. Oh, sorry, I think I'm out of time. Here I just want to show you, as you see here, if you have multiple like the x-axis text they are overlapped very serious. You couldn't see the label here, and then we can change it. Still by the same function. Here, you can. I just change everything. I change the size, the color of abundance, and the sample, and also change the size, color of the text, x text. I also rotate it, because if you have like the overlap series, you want to rotate it a little bit, just to help you to make the label clear. And also sometimes let's see, for the x-axis, I think it's hard to see it here. There is the text, but sometimes I don't like the x-axis text. I want to remove it. So another option, we can remove the text. First we can remove all the. It just give you like we can all remove all the titles, but it's not very meaningful. So, but I just tell you how you have one option to remove all the titles. But next one is to remove the text of the axis. I see here we don't have the text for I, X, and Y axis. Okay, I think the last option is we can also move the legend. Now it's in the right side. We want to move the legend to the right side. Right side is the default one. But now we want to move the legend to the bottom, or just remove the legend. I think for the bottom and one is quite this one I prefer. I like to put the legend to the bottom, because I can make the figure wide. And there are in the code I give some other options you can change. So like here is we introduced facet before, just as here, but here the title of each plot is gray, so it's hard to see. We want to highlight it. In Ggplot 2, you can also highlight it. Here I just give some yellow color. I know it's not very good, but just see you can highlight it. And the last one, just a skill function. Function can do a lot of things, but we don't have the time. We just emphasize one important function is to change the color by skill. Also, you can change the skill by. Definitely, you can change the skill of the data set when you just load in the data set, but we can also change it just for our plot. And here is one interesting thing is, let me see. We can reverse the y-axis. See here is sometimes now the axis is like from lower to larger. Sometimes we want to reverse the axis. That's the option is scale Y reverse. Okay, I think for the improve figure clarity, I'm done. Just tell you have so many options in Ggplot 2. That's why Ggplot 2 is a very powerful tool for visualization, because you can really almost change everything you see in the plot, and you have so many options to do it. Honestly, I think it's so hard to remember all the options you can use. So I usually just Google it, and you will see many notes about how to change something in Ggplot 2. Okay, before our break, any question about this one? Okay, then I think it's break time.
I
Because
couldn't
there's so many.
see.
Uh,
Just one by one, what is every step
okay.
doing?
Okay. Sorry. Here. So basically, I want to give the one specific point a different color,
Right.
and also give it a label.
Right.
So then we need to define two things. So we need to define another group,
Right.
two groups. One group is only one point, the
Right.
point we are interested in,
Right.
and all the others are in the other
Right.
groups. So then when we make the plot, we just and Ggplot just separate it
Right.
from other points.
Right.
That's the first thing we do. Like here, I'm interested in this sample.
Mm-hmm.
Or you can see if you plot if the point is protein, you are interested in one protein.
Right.
And so that's why we highlight. We just say that's a sample.
Just name.
Yeah.
I can name it anything.
Yeah.
It's name of a vector. It's a vector.
No, it's just a 1 point. It's a character, only one.
Oh, it's a character, right?
Yes.
Because it's in straight quotes. Okay.
Yes. So then I make another column in the data set.
Right.
The column I just see if the sample name, if the
Right.
sample is the required sample,
Right.
we just make it highlight. We just
Right.
give it highlight.
Right.
If it's not, we do it's normal and see. Let's run it.
If else.
Yeah.
If else. If sample is highlight sample, then highlighted, otherwise normal.
Yeah. And see now you will have a new column here. So all of them are normal.
Other than the.
Yes. Only the one we are interested in only highlight.
Right.
So then. So actually, in this way, you have already been able to. Sorry.